So it's my great pleasure to introduce Chelsea Walton from Rice University that will tell us about filtered Frobenius algebras in monoidal categories. Thank you, Chelsea.
All right. I'd like to thank the organizers for inviting me to speak here. It's really nice. The talks so far have been really awesome. So this is joint work that's on the archive right now with my grad student, Harshit Yadav. And I want to emphasize that even though he is my grad student, he did half of the work. So he's really, really good. And it was fun working with him. All right. So there are two motivations for this work on filtered Frobenius algebras and monoidal categories. I was raised a ring theorist, and now I'm kind of into category theory. So motivations come from both perspectives. From the ring theory perspective, what I'm interested in are nice algebraic properties that are preserved under filtered deformation. And by this, I mean, all right, if I have a nice filtered algebra over a field K, and I consider its associated graded algebra, I want a statement like, if grade of A is blank, then so is A. Okay, so in this case, A is considered to be the filtered deformation of grade A. So some examples of blank are integral domain. If grade A is an integral domain, then so is A. Blank could be prime, and blank could also be Noetherian as well. So these are really, really nice properties to have in a ring, of course. Some examples of filtered deformations are universal enveloping algebras, Weil algebras, and Clifford algebras, because respectively, or they are filtered deformations of nice rings that we're familiar with, namely the symmetric algebra on the V algebra G that appeared in Sue's talk, symmetric algebra on V, and the exterior algebra on V, respectively. So in particular, all of these algebras, or at least, well, these two are Noetherian domains, and so their filtered deformations are as well. Okay, so that's one motivation for studying filtered Frobenius algebras and monoidal categories. Another motivation comes from the perspective of quantum algebra. If I'm allowed to say that quantum algebra is different than non-commutative ring theory. Okay, so this is all about building Frobenius algebras and monoidal categories. So what is this? A monoidal category, this is a category that has more structure on it. It comes equipped with a bifunctor, a way of sticking two objects together and getting a third object in the category, sticking two morphisms together and getting a third morphism in the category, and also an object in the category that plays a role of a one, so that this triple mimics the structure of a monoid. So you have some compatibility conditions. Now, once you have a monoidal category, you can build algebraic structures in it, like algebras. I mean, algebra in a monoidal category is a triple consisting of an object, A, and two morphisms, M and U, that are your multiplication and unit maps. And you can build other algebraic structures like coalgebras. And also, you can build what's called a Frobenius algebra. So that's a 5-tuple, an object A with these 4 maps here, so that this triple is an algebra, this triple is a coalgebra, and the multiplication and co-multiplication interact via this commutative diagram. So these are really pretty structures. I'm sure many of us are familiar with them over Vec. And in monoidal categories in general, there are lots of applications of these gadgets. They appear in Morita theory, topological quantum field theories, conformal field theories, computer science. They're all over the place. So tying the two motivations together, if we take as our monoidal category to be the category of vector spaces, with the tensor product being tensor over K and the one to be K itself, then Frobenius algebras in this monoidal category are simply Frobenius algebras over K. All right, so there are like 10 different equivalent characterizations of Frobenius algebras over a field. You can pick one. Okay, so those are my two motivations coming from ring theory and quantum algebra. And what do I want to do to blend the two? What I'm interested in is generalizing a result from Bongali from 1967 that says that being Frobenius can be preserved under filtered deformation. So let's take an algebra A that's finite dimensional and also filtered. And it's also connected, meaning the zero filter piece is K. And the statement is that if the associated graded algebra of A is Frobenius, then so is A. So this is a really cool result. I mean, I think it's been hidden for a while. It's not cited much, but clearly I think it's important. It should be used. And what we want to do is generalize this result to the context of Frobenius algebras and monoidal categories. All right, so that's blending the two motivations. Okay, so I'll just give you the main result before we get into the tools we need to build it and how to prove it. The main result is this. Instead of working in the category of vector spaces, we work in a nice monoidal category that's abelian. So you have kernels and co-kernels, and also rigid. You have dual objects as well. And the statement goes like this. We take a filtered algebra in C, whatever that means, that has finite filtration. We want it to be connected, meaning that the zero filter piece is 1. And the result is that if grade of A is a Frobenius algebra in C, then so is A. All right, so I think this is it's a nice, clean generalization. All right, so in order to produce this result, we need to cook up a couple of tools to handle this. And I think these tools are of independent interest. So first of all, we need to lay out some categorical filter graded techniques in this paper. And we also need to think about or consider another characterization of Frobenius algebras and monoidal categories. So at least over a field, there are like 10 equivalent definitions of Frobenius algebras. I can name like 10, a lot of them. But in monoidal categories, prior to this work, there are about 3, and then we add another characterization. Okay, so those are the tools we're going to consider. Any questions so far before I get into the tools? All right. So one tool. It's all about building filter graded structures for our purposes. What we do is we consider a monoidal or build a monoidal associated graded functor. So this doesn't come out of the blue. I mean, we didn't just pull this from the sky. This does build on lots of prior works in the literature, starting with work of Schaumburg in 1996, Artigiani Manini in 2012, and a few papers actually in algebraic topology. And what this allows us to do is take a filtered algebra and construct its associated graded. So let's get into this. We take C, an abelian monoidal category with a biexact tensor product, meaning that the bifunctor is exact in each slot. And what we want to do is consider 2 categories consisting of filtered objects in C and graded objects. For fil C, objects are just objects in C that come equipped with a filtration functor. It assigns every natural number to an object in C so that the colimit of this functor recovers X. Morphisms in this category, just morphisms in C that preserve this filtration. And this category is also monoidal by taking as the object to be the tensor product of each of the objects. And the filtration functor is just given by the day convolution of fx and fy. Okay, so this is a nice monoidal category. We can build algebras in it. We call such algebras filtered algebras. Grade C. These consist of objects that have a nice graded decomposition as you would expect. Morphisms preserve the grading, and the tensor product respects the grading as one would expect. And we build the associated graded functor by just sending a filtered object given by A and its filtration functor to this coproduct of co-kernels here. In particular, you have that this category in knot, it's a category that has its object's natural numbers, including 0, and arrows where if I is less than J, we get an arrow from I to J. So we have a morphism given like so, and we take the co-kernel of such maps and build our graded algebra. So this is a nice functor. We put a monoidal structure on it. And again, what the monoidal structure allows us to do is send algebras here to algebras here. So that's our first result. Okay, second result. We need another characterization of a Frobenius algebra. Now, recall that in a monoidal category, we have that a Frobenius algebra can be defined as this 5-tuple consisting of an object A and several maps that satisfy this diagram here and these axioms. But what we cook up is a Frobenius form characterization of Frobenius algebras. So we have that in algebra A is Frobenius if and only if there is a form or a morphism going from A to the 1, so that any left or right ideal of A that factors through the kernel of this map must be 0. So if you're familiar with Frobenius algebras, this is exactly what you want. This is one of the definitions of the Frobenius algebra over a field. So we like this characterization as opposed to this one because we're interested in generalizing Bongali's result, and she proves her result by using this characterization. So it's just easier to produce this result and mimic her proof rather than revamping her proof. Okay. So now, how do we prove our main result? Again, what is it? You take a C, an abelian rigid monoidal category. You have a connected filtered algebra in C with finite filtration. And the statement is that if grade of A is a Frobenius algebra in C, then so is A. Okay, so here's a sketch. I mean, the paper is really technical, but I tried to just break it down so that it's easy to understand here. So we take a filtered algebra. That's an algebra that comes equipped with a filtration. And it has a finite filtration. So what that gives us is that A is actually identified or isomorphic to, well, the nth piece of the filtration on A for some n. Right, so that's some object in C. Now what we want to do is we want to build a form on A that's going to serve as a Frobenius form. So we take a morphism going from A using this isomorphism here, and considering the quotient from FAN to FAN mod FAN minus 1. Okay, so the co-kernel of the map going from this to this. This is actually going to be isomorphic to 1 because A is connected. So far we've used all of our hypotheses. We've used filtered finite filtration here and connected here. All right, so now what we want to do is show that this eta is a Frobenius form. So let's take an ideal of A so that it factors through the kernel of this morphism eta via map phi. And now by tool 2, our characterization of Frobenius algebras, it suffices to show that I is 0. Okay, so now what we need to do is consider the hypothesis of the theorem. Take grade of phi, we get this map here. We can take grade of algebras and ideals and get ideals and algebras via tool 1, our associated graded functor. And then we have to show that grade of phi then factors through the kernel of a Frobenius form on A, or grade A. Now by tool 2, we get that grade of I is 0, and then we can conclude that I is 0. All right, so that's how we prove our theorem. There's a lot buried in between the lines here, but that's a sketch. Okay, so you might be wondering about a source of examples. I mean, I mentioned some examples of filtered deformations at the beginning of the talk, but the only finite dimensional ones are, Clifford algebras being filtered deformations of exterior algebras. So naturally, we will want some sort of categorical version of this. So we do discuss braided Clifford algebras in our paper. This is what we have so far. So recall for Beck, what is a Clifford algebra? We take a vector space V, we take a symmetric bilinear form, and a Clifford algebra defined like so is a filtered deformation of the exterior algebra. Since exterior algebras are well known to be Frobenius, we get that their filtered deformation is also Frobenius as well. And this is due to Bengali, this is her result, or our main theorem in a case where C is VEC. Okay, so what we want to do is consider categorical version of this, or braided version of this. And this is sticky. This is stickier than I thought it would be. We hope that anybody who's interested in this will attack the problem that we pose. So what we do is we need to take a symmetric monoidal category. So this is a monoidal category that comes equipped with some natural isomorphisms that allow you to swap across the tensor so that when you swap twice, you get the identity here. For example, the category of vector spaces is a symmetric monoidal category where you literally just flop across the tensor. And in a symmetric monoidal category, there is a notion of a braided or a version of an exterior algebra due to Bespalov in 2 papers of his and co-authors. So we want to use it because there is a braided exterior algebra out there. The trouble is that actually defining what a braided exterior algebra or braided Clifford algebra is quite difficult combinatorially. It's the subject of another paper. And so we pose a very careful problem on how to do this, hoping that somebody will attack it so that we have these algebras. But what you would do is you would take a form on V tensor V so that it's symmetric in the braided sense. We use some combinatorics with shuffle products, and again, we have a sketch in the paper of how to do this. But once you attack the problem, you have the definition or filtered deformation of this braided exterior algebra given by the braided Clifford algebra, and you get that these algebras are Frobenius. So under certain finiteness conditions, we show that the braided Clifford algebras, braided exterior algebras are always Frobenius. And if the problem is resolved, i.e. if these Clifford algebras exist, then they are Frobenius as well by our main theorem. Okay. Some other further directions that might be of interest to folks. Again, I have these 2 motivations here coming from ring theory, taking algebraic properties and preserving them under filtered deformation. We've talked about preserving Frobenius. And from the perspective of quantum algebra, building Frobenius algebras in monoidal categories. And here's our main result, blending the 2. Now, from the perspective of ring theory, it might be interesting to consider other ring theoretic properties that are nice, especially those that are preserved under filtered deformation. Is there like a nice categorical version of being a domain, prime, Noetherian? I mean, I don't know about domain. I think that will be kind of hard, but I think prime and Noetherian could be done because this involves ideals and chains and inclusions. I think this could be done. So the question now is, well, first of all, define these notions in a categorical context and study when they are preserved under filtered deformation as we laid out above. Okay, so we've done this for for Frobenius algebras. What about other properties as well? Another problem that might be of interest to folks from the quantum side is that, again, Frobenius algebras and monoidal categories are quite important, especially in topological quantum field theories, whatever these are. I mean, it's a functor that takes in a topological manifold and spits out an object in C. So it gives us a way of telling apart manifolds in this categorical way. Now, what's nice is that if you take the 2-dimensional versions of these topological quantum field theories, they go hand in hand with Frobenius algebras, commutative Frobenius algebras in C. So if you see a commutative Frobenius algebra walking down the street, you can grab it and build one of these machines here. So this led to like a surge of interest in Frobenius algebra, especially in the mid-90s. Now, graded filtered Frobenius algebras in C, they also play a role in quantum field theory, namely in open-closed topological quantum field theories due to work of Lauda, Pfeiffer, and others that we cite in our paper. So of course, it would be worth studying the connection between these theories and our main theorem. We understand the Frobenius algebras, but what happens here? And as usual, I try to always end a little early because why not? But that's all I have to say. And hope you enjoy the report on the work. Thank you.